We're going to begin our study of blood by looking at the red blood cell, also called the erythrocyte. These are very small cells with a biconcave disc shape. So if we break this down, bi means two, concave means like it's dented in. So if you can see here, it dents in, here it dents in. That's your biconcave. And then disc means that it's a flat circle. They also are technically not cells. The reason they're technically not cells is because they lack a nucleus. And one of the overriding themes in anatomy and physiology is that form follows function. So their form is to be this small biconcave disc with no nucleus. Their function is to carry oxygen and carbon dioxide and to fit through capillaries. Capillaries are very narrow, tiny blood vessels, and they're hard to get through. So red blood cells have to be able to fit through capillaries. So form follows function. So their form, their structure, goes along with their job. So we're going to break that down and look at it. If we look first at the delivering oxygen and carbon dioxide. Erythrocytes have hemoglobin. This is a protein molecule inside of them that binds oxygen and carbon dioxide. In fact, inside each one of these erythrocytes, there are about 280 million hemoglobin molecules. Each one can bind either 4 oxygen or 4 carbon dioxides. The next feature that helps them to deliver these is the fact that they don't have a nucleus. So anucleate means no nucleus. The nucleus is typically the largest structure in a cell. So the nucleus takes up a lot of room. When erythrocytes start out, they do have a nucleus, but as they mature, they lose it. And by losing their nucleus, they make more room for hemoglobin. So this maximizes the oxygen and carbon dioxide that they can carry. Another important feature is that they have no mitochondria. Let's think about this for a few minutes. Erythrocytes do not have mitochondria. Now, they're still living and they still need energy, but they can make ATP by glycolysis, which doesn't use the mitochondria. Think about the significance of not having mitochondria and how that allows them to deliver more oxygen. Let's imagine for a moment your erythrocyte, which we can put RBC to abbreviate red blood cell, is like a pizza delivery guy. The oxygen is the pizza, and your cells are the hungry customers. So you call up, you order a pizza to have delivered to your house. The pizza delivery guy is hungry. So as he's on his way to your house, he goes ahead and eats a couple slices of your pizza. So when you get your pizza delivered, there's some missing because he ate it. You probably would not like this. There'd probably be no tip and a phone call to the pizza place. It's the same idea here with your red blood cells in delivering oxygen. Their job is to deliver oxygen to your cells. Not use it themselves. Well, if you think back to chapter 3 and what you learned about cellular respiration, the mitochondria is what uses oxygen. Glycolysis takes place outside the mitochondria and does not use oxygen. The mitochondria with the Krebs cycle and electron transport is where oxygen is consumed. So if you take away the mitochondria, then it becomes impossible for the cell to use oxygen. So the significance of not having mitochondria means that they can't use oxygen. This way, they instead carry it and give it to other cells. And a fourth feature that goes along with delivering more oxygen is the shape, the biconcave disc. If we come back up here and look at the picture, notice how it's kind of flat. You've got oxygen in here. It has to get out, it has to get in. It has to get in and out quickly. Imagine instead if you had a sphere, if you had a cell that was like a basketball. The oxygen would have further to go to get in or out. By having this thin, flat cell, the oxygen doesn't have very far to get to a surface. There's always a surface to get in and out through nearby. So the biconcave disc allows for faster diffusion in and out. So it's quick for the oxygen to diffuse in, to diffuse out, as opposed to if the cell were spherical. Okay. Our other function is that they have to fit through capillaries. So let's look at how they fit through capillaries. So for one, they are very small. We mentioned this before. Red blood cells are 7.5 micrometers. To give you a comparison, a typical cell in your body is about 30 micrometers. So they're much smaller. They're one of the smallest cells you have. This obviously helps them fit through small, narrow capillaries. That biconcave disc, again, is an important feature. This allows them to form a roulet. Take a look in your book. There's a photograph of this in chapter 18. This is where the red blood cells stack on top of each other, kind of like a stack of coins. This way they can squeeze through the capillary without getting tangled up with each other. And then finally, they fit through the capillary with the help of spectrin. Spectrin is the protein that makes their framework. This protein is very flexible. So imagine like the 2x4s in a building. They form the framework. Imagine if they were bendy and flexible and you could bend that structure. That's what it's like with your red blood cells. This allows them to bend in order to squeeze through the capillaries. All right, so there are the main features of a red blood cell and how those features help it do its job. So now we can move into a little more detail of the red blood cell and look at the hemoglobin that's inside of it. So remember, you have 280 million hemoglobins inside each erythrocyte. A hemoglobin is made of different parts. All the parts here that are brown and tan are the globin part. The globin part is protein. And this is the part that binds carbon dioxide. Notice you have 4 globins. Each one can bind a carbon dioxide, so you can have a carbon dioxide on each one of these. Then in the center, you have this small blue and red thing. That is the heme. The heme has the red in there, which is the iron. The iron is what binds the oxygen. So you have iron on the heme. This is what binds oxygen. And again, you have 4 of these. So each one of those can have an oxygen on it. It's important to note that you can't have oxygen and carbon dioxide at the same time. So the hemoglobin can either have oxygen or it can have carbon dioxide. It cannot have both at the same time. But that's okay, because what happens is you go in the lungs and you pick up oxygen and you drop off carbon dioxide. Then you go to your cells and you do the opposite. You drop off the oxygen and you pick up the carbon dioxide. So it doesn't really need to carry both at the same time anyway. If we look a little more at this bond between iron and oxygen, it is a weak bond. So there's pros and cons to this. The pro of this is that it easily gives up the oxygen to the cells. Remember, the whole point is you want to give oxygen to the cells. If it were a strong bond, it would hold on to the oxygen and not give it to the cells. So the good thing about that bond being weak is that it will give the oxygen to the cells. The bad thing about this is what makes you susceptible to carbon monoxide poisoning. So the con is that the oxygen can be replaced with carbon monoxide. So carbon monoxide and carbon dioxide are two different things. CO is carbon monoxide. This is very dangerous. So like you hopefully have a carbon monoxide detector in your house. This is why if you start your car, you open the garage first. This is why you don't use a grill inside, because the grill gives off carbon monoxide. It is a result of combustion. Anytime something is burned. So like gas in your car, the charcoal in your grill, they're all giving off carbon monoxide. You need a carbon monoxide detector in your house because your furnace, and if you have a gas stove, a gas water heater, gas appliances, they all have the potential to give off carbon monoxide. And here's a little tip of how you can tell. When you look at your gas stove, you see the flame, or if you have a gas furnace, you can look inside of it and see the flame. The flame should be blue. If the flame is blue, that's good. That's a clean flame. So there's no carbon monoxide. If you ever look at your stove or your furnace or whatever, and the flame is yellow, that is bad. Yellow means that it's giving off carbon monoxide. So you want to turn the appliance off, get out, and call somebody to come fix it, because you don't want to get carbon monoxide poisoning. So what happens with the hemoglobin is when you have both carbon monoxide and oxygen, and here's your hemoglobin, they will compete for it. Since oxygen forms only a weak bond, the carbon monoxide can kick it out. So if you have oxygen on here, carbon monoxide comes along. It's kind of like a big bully. And that's a weak bond holding the oxygen to the heme. So the carbon monoxide kicks the oxygen out, and then it takes its place, binding to the heme. This means that now you're not delivering oxygen to your cells. Okay, so think about what you do with oxygen. Oxygen is used by mitochondria to make ATP. If you don't deliver oxygen to your cells, then your cells can't do cellular respiration and make ATP. They'll have to switch to fermentation. And remember, when you switch to fermentation, you only get 2 ATP instead of 36, like you get when you do have oxygen. And you get lactic acid building up. So one of the early warning signs of carbon monoxide poisoning is that you feel tired. And if you do get carbon monoxide poisoning, the important thing to do is get outside and get fresh air right away. If you stay in there and you keep breathing the carbon monoxide, you'll eventually die. So make sure you have a carbon monoxide detector in your house and pay attention. Get outside if it goes off. So that's the basics of hemoglobin. That's the molecule that you have in your red blood cells that is delivering the oxygen and some of the carbon dioxide, but not all. Now let's talk about homeostasis in your blood. So remember, homeostasis is an overriding thing that's important for many things in your body. The aspect we're going to look at here is oxygen and viscosity. So for oxygen, you need your blood to carry lots of oxygen. The more oxygen, the better. So this means having lots of red blood cells. The more red blood cells you have, the more oxygen you can carry. But red blood cells also increase the viscosity of your blood. So the more red blood cells you have, the thicker your blood is. Viscosity means how thick your blood is. If your blood gets too thick, then you won't be able to pump it and it won't flow through your blood vessels. So you have to find a balance between these. You need a balance where you have lots of red blood cells to carry oxygen, but not too many that your blood gets too thick. So your kidney is what maintains this balance. Your kidney filters your blood. As it does, it monitors the oxygen level. So we have here your kidney. It's filtering your blood, and as it is, it monitors your oxygen. If it notices that oxygen has dropped, so if your kidney detects a drop in oxygen, let's see what could cause oxygen to drop. So for one, red blood cells don't live forever. They live about 121 days and then they die. So whenever you have red blood cells dying, your oxygen level goes down. You could also get a cut and have blood loss. Anytime you lose red blood cells, you lose oxygen carrying capacity. If you start to exercise more, then you're going to be using up more oxygen, and so your oxygen level will go down. Or if you go to high altitude, right, such as going up in the mountains. Maybe you've heard of altitude sickness. People who aren't used to being up in the mountains, they go up in the mountains and they get sick because they don't have enough oxygen up there. The higher up you are, the less oxygen there is in the air. So any of these things could cause your oxygen level to decrease, and your kidney is going to detect this. When your kidney detects a drop in oxygen, it secretes a hormone called EPO. This stands for erythropoietin. So your kidney detects a drop in oxygen, it secretes erythropoietin. Blood cells are made in your red bone marrow. You learned this in Chapter 7. Remember that you have red bone marrow like in your skull, in your hips, in your vertebrae. It's pretty much in your torso area. EPO stimulates that red bone marrow. And it will cause the red bone marrow to make more red blood cells. So now you get more red blood cells. Well, if you have more red blood cells, you've just increased the oxygen capacity of your blood. And now you have negative feedback. This increase cancels out the decrease. And so the EPO level goes down, you stop making red blood cells, and you're at homeostasis until the next time your oxygen drops. This way, you always have enough red blood cells to carry enough oxygen for you, but not too many that you make your blood too thick and then it won't flow. The other factor, besides low oxygen, that can stimulate the kidney to do this is testosterone. Testosterone will stimulate the kidney to secrete EPO. And then that will stimulate the bone marrow to make red blood cells. And then you will have higher oxygen. So the higher your testosterone level, the more red blood cells you have. So in general, men have more red blood cells than women. And that hematocrit is the measure of your red blood cells. So men tend to have higher hematocrit. The other difference you can see in hematocrit between people is based on where they live. Remember that high altitude has less oxygen in the air. So people who live at high altitude, like someone in Colorado, is going to have higher hematocrit than someone who lives at a lower altitude. At high altitude, there's less oxygen in the air, so your body has to compensate by having more red blood cells. Okay, so this process of the EPO stimulating bone marrow to make red blood cells, which affects how much oxygen you can carry, is used and manipulated. Athletes want to have lots of oxygen. Remember, you use oxygen to make ATP. When you have oxygen, you get 36 ATP. When you go into oxygen debt, you only get 2 ATP. So the more oxygen you have, the more ATP you can make. So having lots of oxygen means that they will have lots of energy. so their muscles can work better with all that energy. So a couple of things that can happen. Athletes can train in Colorado. Colorado is a popular place, especially when it's Olympics time. A lot of the Olympic athletes go to Colorado to train because Colorado is high altitude. So there is less oxygen in the air. So when you go there, you will get less oxygen. That means there will be less oxygen in your blood, which will cause your kidney to secrete more EPO, which will cause your red bone marrow to make more red blood cells. And remember, they live for 120 days. So for about the next 3 months, you will have extra oxygen carrying capacity in your blood. So if you go up to Colorado, spend a few weeks there training, get that extra red blood cells, and when you come back down to lower altitude, you will still have those extra blood cells for a few months. The other thing, the second one here, is illegal. This is blood doping. So there's two ways to blood dope. There's kind of the old-fashioned way and there's the more modern way. This picture shows the old-fashioned way. In the old-fashioned way, you would remove some of your own blood. So remember, blood loss will make your oxygen level go down. So by removing your own blood, your oxygen level in your blood goes down. So your kidney will detect this and secrete EPO. This causes your red bone marrow to make more red blood cells. So this just gets you back to your starting point. You replace the ones you lost. Here's the trick, is when you removed your blood, you didn't just throw it away. You put it in the refrigerator. So now that you've replaced the ones you lost, you re-inject the blood you removed. Now you have extra red blood cells. And those extra red blood cells will give you more oxygen so that you can have more ATP for your athletic event. The new, more modern way to do this is now they have EPO that you can just inject. So you can get a hold of some EPO and just inject it into yourself. You bypass your kidney, and that EPO go tell your red bone marrow to make more red blood cells, and your hematocrit will go up. The dangerous side effect of this, people can die from doing this. The danger is that you will make too many red blood cells and you will increase the viscosity. So you will make your blood too thick. And then you can clog your vessels or even give yourself a heart attack. If you go to Colorado, you're going to get some more red blood cells, but your body is, remember, maintaining balance. It's not going to make your blood too thick. If you are injecting yourself with things, you lose that homeostatic control, and you could accidentally make your blood too thick and kill yourself. Now we'll look at a problem you can have with blood known as anemia. Anemia is when you lack red blood cells or there is some problem with your red blood cells. Red blood cells are critical for carrying oxygen. And if you have anemia, you're going to have trouble carrying enough oxygen in your blood. There are many different types of anemias and things that can cause it. And your book has a page that goes through and describes several of the different anemias. For example, most people know about iron deficiency anemia. Most people are familiar that if you don't get enough iron, you can become anemic because you need iron in order to make hemoglobin, and then you won't have enough hemoglobin, your blood cells can't carry enough oxygen. There's also, if you lack folic acid or vitamin B, that you can have problems with making blood cells. The one we're going to focus on here is sickle cell anemia. Sickle cell anemia is genetic. And then when we get to the chapter about the digestive system, we'll talk about pernicious anemia, which you can read about that now in chapter 18, and it'll come up again in a few weeks when we get to chapter 26, because that one's related to the stomach. So for genetic, remember genes code for proteins. And you have a gene that codes for a protein that ends up determining the shape of your red blood cell. It's the beta globin protein. So there are two versions of this gene. A is the normal gene. And if you have this gene, it will code for a protein that makes your blood cell the biconcave disc. And if you remember, that's the shape you want red blood cells to be, the biconcave disc. Then there is S. S is the mutant form. And this one codes for a protein that causes the red blood cell to have a sickle shape. So sickle, if you're not familiar, if you think of like old pictures you've seen, like farmers before there was such thing as tractors, they would use a sickle to harvest their crops. Or like if you've ever seen the cartoon like Figure of Death and he's carrying that tool, that's a sickle. So a sickle is a sharp tool that's shaped like this, and it's on a stick. So that's where the word sickle comes from. So you can see here's the sickle cell. It has kind of that curved shape like a sickle. So there's two versions, the A and the S. If you have AA, remember everybody gets 2 copies of a gene because you have 2 parents, one from your mom, one from your dad. If both your mom and your dad give you the AA, you will have biconcave disc. And all is well. If you get SS, each parent gives you an S, you will have sickle cell anemia. That would make your cells like this, sickle-shaped. And as you can see, sickle-shaped cells don't do well. They get blocked in capillaries. You remember one of the features of red blood cell and the biconcave disc is it helps them fit through your capillaries. Well, if they don't have that biconcave disc, you get blockages in blood flow. Also, these cells have a short lifespan. So you're going to block blood flow. A typical red blood cell lives 120 days. These cells have a much shorter lifespan. They live less than 120 days. And you get anemia, you don't have enough of them because your body can't keep up with replacing them. Your bone marrow can't make them as fast as they die. So you end up with fewer red blood cells, and the ones you have are shaped wrong and they clog your blood vessels. So this is a fatal condition. We do have modern medical treatment that can extend your life if you have sickle cell anemia, but it is difficult to live with. Then there's the heterozygote. Heterozygote means you have two different genes. One parent gives you the A, one parent gives you the S. If you are a heterozygote, you have what's called sickle cell trait. This is a very unique situation. So this is a case of codominance. One gene is not dominant over the other. They're both dominant. So here, if you have sickle cell trait, most of the time the standard is for your cells to be biconcave disc. So you're going to be going along just fine with your biconcave disc cells. There are certain conditions that can cause them to sickle. So if you have low oxygen, if you become dehydrated, or if you suffer a trauma like being in a car accident or something like that that puts your body through a trauma, your cells can sickle. So they will change shape. The cell can go back and forth between being that normal biconcave disc or being sickled. So if you have the trait, your cells can go back and forth, changing shape. As long as you have plenty of oxygen, you're not dehydrated, and you're not going through a trauma, your cells are going to be biconcave disc. And a lot of people who have this can go most or all of their lives with never having their cells sickle. They'll just stay the biconcave disc. So you can easily survive having sickle cell trait. This is Ryan Clark. He was a football player for the Pittsburgh Steelers. And when he was in college, he had a game in Colorado, which Colorado is high altitude. And high altitude means low oxygen. When he went to this game in Colorado, he got really sick and he ended up in the hospital. And at first they didn't know what was wrong with him. Well, then they figured out that he had sickle cell trait. So he had made it all the way into his college years through his entire childhood and never even knew he had sickle cell trait until he went to some place with high altitude and low oxygen. After that, he recovered and he went on and finished his college football career, went on to have a professional career, and he just couldn't play the games in Colorado. So if the Steelers went to play the Broncos, he had to sit out that game. And as you can see, Ryan Clark recovered. Once you get more oxygen, your cells go back to being round. So if you have sickle cell trait, you have the biconcave disc. Then if you get low oxygen, you will sickle. But as soon as your oxygen returns to normal, you go back to the biconcave disc. Your cells go back and forth. And if the time that they're sickled is a very short period of time, it doesn't actually do any harm to you at all. So there is a correlation between sickle cell anemia and another disease, malaria. Here is a picture of red blood cells. And this little yellow thing inside is the malaria parasite. So you've probably heard of malaria before. Maybe you know that it's spread by a mosquito. Malaria is a parasitic disease that is spread by the Anopheles mosquito, and it is very common in Africa. There is a connection between sickle cell anemia, and malaria. As you can see, malaria infects the red blood cells. And when it does, it makes your oxygen level drop. If you are an AS person and your oxygen level drops, your cells will sickle. But the parasite is inside this cell that is sickling. When the cell sickles, it kills the malaria parasite. Now you don't have malaria. And your oxygen goes back up, so then your cells return to biconcave disc. So if you are an AS person, you're sitting here, you have your biconcave disc, a little mosquito comes along and it bites you and it gives you malaria. Now you have the malaria in here, which causes your oxygen to drop. Now that your oxygen drops, your cell sickles, and when it does, it kills the malaria. Now that the malaria is dead, your oxygen goes back up, and your cell goes back to being round, and it is malaria-free. So you are all good. It wasn't sickled long enough to make you sick from having your cells sickled, and you don't have malaria. So there is a protective function of sickle cell trait. Having sickle cell trait protects you from malaria. So if we look at a scenario, if you live in a place where there is a lot of malaria, you could have 3 different options of what genes to have. If you are AA, you might die of malaria. Millions of people die of malaria every year. If you are SS, you will probably die of sickle cell anemia. But if you are AS, you get the best of both worlds. That's just enough to protect you from malaria, but not enough that you die of the anemia. So you survive both. And then these are the people who go on to reproduce and pass on their genes. So in an area where there's malaria, the most likely people to survive are the people who have sickle cell trait. So that's why there's this strong correlation between areas where you have malaria and areas where people have sickle cell trait. If you've ever wondered why poop is brown and pee is yellow, then today is your lucky day. You are about to find out. And it has to do with your red blood cells. So if you'll remember, a red blood cell has a lifespan of about 120 days. The reason for this limited lifespan is because of spectrin. Think back to earlier in the lecture. Spectrin is the protein that gives the red blood cells their flexibility. Remember how they have to squeeze to fit through capillaries, and spectrin is that flexible protein framework that allows them to do this. Well, after about 120 days, the spectrin breaks down. and they start to lose their shape. So you need to get them out of circulation. You don't want misshapen red blood cells flowing through your capillaries. So you have two organs that are responsible for this, the liver and the spleen. So as blood is flowing through the liver and the spleen, they are removing old red blood cells that are in danger of getting misshapen and clogging your capillaries. Then within these two organs, you have cells called macrophages. So here's your macrophage. Macrophage is a type of white blood cell. And these cells, you can see there's the red blood cell. They eat the red blood cells. So this is called phagocytosis. So they will actually engulf and break down the old red blood cells. And when they do, they break them down into three parts. So we have here the globin. So remember, that's the protein part. So from the macrophage here, when it's breaking it down into these three parts. So the first one is the globin. Remember, this is protein. Well, if you think back to chapter 2, protein is made of amino acids. So that globin is then broken down into its component amino acids. And amino acids are valuable to your body. So those amino acids just go into your blood and they are recycled. So just like you eat protein to get amino acids, you're also breaking this protein down. So here you can see, here are the amino acids from that globin, and they're being recycled. The next part that you get is the iron atom. So you extract the iron from the hemoglobin. Your body will also recycle the iron. So the iron is going to go to your liver where it's going to be stored. And then when your bone marrow needs iron to make new red blood cells, it sends it to your red bone marrow. So most iron is recycled. So most is saved in the liver, then sent to the red bone marrow to be made into new hemoglobin. You do have a little bit of iron loss. That's why you do need some iron in your diet. So your iron losses are through sweat. There's a little bit in urine, and there's a little bit of iron lost in feces. Also, anytime you lose blood, if you get a cut, you're losing the iron that's in that blood, or like women need higher levels of iron in the diet because of the monthly menstrual cycle. There's a lot of iron loss with all that blood loss. So you do have some losses in sweat, urine, feces, and blood loss. Then the third part is the heme. So remember, that was another component of the hemoglobin. The heme has a long, interesting journey. So the heme is converted to bilirubin. You might be familiar with bilirubin if you've ever heard of jaundice. So jaundice is a disorder where you get too much bilirubin building up in your blood. So it's converted to bilirubin, which bilirubin is yellow. That's why jaundice makes you turn yellow. And this is put into your blood. So you have bilirubin flowing around in your blood. Well, as it's flowing around in your blood, your liver filters it out. So you're going to have here the bilirubin goes into your blood, and then it goes to your liver. That's why jaundice is a disorder of the liver. If your liver is not working, then it's not filtering that bilirubin out of your blood, and that's how you get jaundice. Okay, now that this bilirubin is in your liver puts it in the bile. Liver makes bile. You've probably heard of bile. It's made by your liver, it's stored by your gallbladder, it's sent to your intestine when you eat, and it helps your body digest fats. And you may have seen it like sometimes when you're really sick and you're throwing up a lot and it looks like you threw up some egg yolk. That's your bile. So now you have the heme converted to bilirubin is in your bile. Bile goes to your small intestine. So here we are in the bile, and it goes to your intestines. So your liver makes the bile, sends it to your gallbladder to store. When you eat, your gallbladder sends it to your intestine. So now the bile goes to your small intestine. Here it's going to be converted to urobilinogen. So now you have what used to be your heme, but is now urobilinogen in your small intestine with your food. Well, your small intestine absorbs food into your blood. And as it does, some of that urobilinogen is absorbed into your blood with your food. So some of it is going to be absorbed into the blood with your food. So now some of that goes back into your blood. Once it's in your blood, it's converted to another chemical called urobilin. So now you have urobilin flowing around in your blood. Remember, this started as the heme from a dead red blood cell. Now your kidney filters it out. So urobilin is filtered out by your kidney. And then it becomes part of your urine, and it is the yellow component of urine. So the color of urine being yellow, it's not about what you eat or what you drink, it's from your dead red blood cells. Okay, now remember I said that was part of the urobilinogen. Not all of it gets absorbed back into the blood with your food. Some of it passes with the waste into your large intestine. And if it does this, then it's converted to another molecule called stercobilin. It then stays in the large intestine with all the waste as it incorporated into the feces. And stercobilin is brown. So this is the brown part of feces. So then some of it leaves with the feces. And stercobilin, once you convert from urobilinogen to stercobilin, it goes from yellow to brown. So that is what happens to your old red blood cells. They live 120 days. Then their spectrum starts to break down. They lose their shape. So your spleen and your liver pull them out of circulation. Macrophages in your spleen and liver break them down. You recycle the protein, you recycle the iron, the heme you turn into bilirubin, you put that in your blood, then your liver pulls it out, puts it in the bile, sends it to your intestine. It's converted to urobilinogen. Some of it comes back to your blood with your food, then your kidneys filter it out and it becomes the yellow component of urine. Some of it stays in your intestine with the waste and it's converted to stercobilin and becomes the brown component of feces. Let's take a look at blood type now. Maybe you know your blood type, and if not, you'll have a chance to determine your blood type in class. So blood type is genetic. And remember, genes code for proteins. So you have proteins on the surface of your red blood cells called antigens. Lots of cells have antigens. If you've taken microbiology, you learned about them in there. When we study the immune system, we're going to learn about antigens. So it's not just red blood cells that have antigens. But the ones on your red blood cells are what determine your blood type. And if you remember from chapter 2, proteins are all about shape. So these antigens come in different shapes. And your blood type is which shape antigens you have on your red blood cells. So there are 2 different genes that give you antigens on your red blood cells. There is the ABO, and there is your Rh positive or negative. So for ABO, you can have the A gene will give you the A antigen. There is the B gene, codes for the B antigen. And the O gene codes for no antigen. So O just means you don't have an antigen. There is no such thing as an O antigen. O just means you don't have it. And for Rh, if you have capital D, that codes for having the D antigen. Or you can have lowercase d, which like O means no D antigen. We're going to fill out this chart, and as we fill out this chart, you'll start to see the pattern and it'll start making a lot of sense. So first for the genetics, it's 2 genes. So you have the ABO and you have the Rh. Let's say you either have AA, means each parent gave you an A allele, or you could have AO. One parent gave you an A and one parent gave you an O. If that is the case, you will have A antigens on your red blood cells. So A is dominant, O is recessive. If you have 2 capital Ds, so each parent gave you a capital D, or you have one big, one little, then you would also have the D antigen. If you have A and D antigens, your blood type is A positive. Let's say you have, again, either AA or AO, but this time each of your parents gave you a lowercase d. In this situation, you would have the A antigen, but because both of your Ds are the lowercase recessive ones, you would not have a D antigen. So all you have is A's. This is A negative. Let's do the same thing with B's. If you have two B's or a B and an O, you get B antigens. B is dominant over O. If you have two capital D's or if you're heterozygote, you get the D. This is B positive. If you get a BB or a BO and then two lowercase d's, you just have B's, and this is B negative. Okay, are you starting to see the pattern here? Let's suppose one parent gives you an A and the other parent gives you a B. Well, A and B are codominant. So you would make both types of antigens. If you have both the A allele and the B allele, you'll have both the A and B antigens. Let's say your parents give you at least one big D, then you would have D. So you would have all three antigens. This is AB positive. If one parent gives you an A and the other a B, and they each give you a lowercase d, you have A's and B's, but no D's, so you're AB negative. O is the recessive trait. So in order to have type O blood, you have to get an O allele from each parent. And remember, there's no O antigen. That just means you don't have A or B. If you have at least one big D, you would have D's. This is O positive. And if each parent gives you an O and each parent gives you a lowercase d, you have no antigens at all, just this naked red blood cell. This is O negative. So that's how you determine the blood type. It's based on which antigens you have, which are coded for by your genes. Now we can look at antibodies. Antibodies are made by your immune system against foreign antigens. So antibodies are proteins. And again, proteins are all about shape. They are shaped to fit to an antigen. So you can think of antibodies and antigens are like a lock and key. So remember, you're going to have antibodies against whatever antigens are foreign to you. If you have A positive blood, that means you have A and D antigens. You will therefore have B antibodies because B is foreign to you. If you're A negative, you have A antigen. You do not have B or D. So B and D are foreign to you, you'll make B and D antibodies. If you're B positive, then you do not have A antigens. They are foreign to you, so you make A antibodies. Your immune system doesn't like any antigens that are not naturally a part of your body. It makes antibodies to attack them. B negative has A and D antibodies. AB positive, notice if you're AB positive, you have all three, A, B, and D. Nothing is foreign. AB positive people do not have any of these antibodies. AB negative has D antibodies. O positive has A and B antibodies. O negative, because they don't have any antigens at all three of them are foreign. So they would have all three antibodies. Antibodies are important when it comes to doing transfusions. So transfusion, when you can put blood from one person to another, and a lot of times you need to do this in order to save somebody's life. This is the antibody. These are the antigen. In this case, notice the antibody does not match the antigen. So here, see this is a triangle shape, and these are round. So in the top one here, we have no match. This lock and this key do not go together. The antibody does not fit to the antigen. So the antibody leaves the blood cells alone. So we could say that this is an A antigen and that the antibody is a B antibody. They don't fit together, so they leave each other alone, and everything's fine. That's what you want. You want your antibodies leaving your cells alone. Down here, though, notice we do have a match. Their shapes fit. So if this is the A antigen, and this is an A antibody, they fit together. And notice that an antibody has two binding sites here. So it will bind to two red blood cells. So one antibody binds to two red blood cells. And this goes around. So if you had a red blood cell here, you had an antibody binding to it, and another one here. Well, then you could have another antibody here binding, and another blood cell here. And you could have an antibody here, and a blood cell here. And it could keep going. And what you end up with is a big clump of red blood cells. And this clump is called agglutination. Now, it's important not to mix up agglutination and coagulation. Students tend to want to do that. Agglutination is when an antibody binds to red blood cells and causes them to form a clump. Coagulation is when you get a cut and you make a blood clot so you stop bleeding. Different things. Don't mix them up. So when you're doing blood transfusions, you want to avoid agglutination. Agglutination is deadly. If those blood cells are all clumped up, they're going to clog your blood vessels, the blood's going to stop flowing, and you will die. So you don't want this. So when it comes to doing blood transfusions, you have to avoid agglutination. So let's look at which things can be transfused. Let's say you have type A positive blood. And you need a transfusion. We want to know what kind of blood we can put into you. If you have A positive, that means that you have B antibodies. Well, if you have B antibodies, that means you will attack and agglutinate B antigens. Agglutination is a bad thing. You don't want it. So if you will agglutinate B antigens, that means we cannot put any B antigens into you. So you must avoid B antigens. So let's look through the list and see what you can get. So we'll start off with A positive. There's no B antigens on that blood cell. So A positive is good. You can always get your own blood type. If we look at A negative, again, no B antigens there. So you can get A negative. If we look at B positive, well, it has B antigens. So that one's out. B negative has B antigens. That one's out. ABs, the AB positive and AB negative, both have B antigens. So those are out. The O's, neither one have any B antigens. So those are both good. So if you have A positive blood, there's a list of blood types you can receive in a transfusion. Let's do another example. Let's do B negative now. If you have B negative blood and you need a transfusion, this means that you have A and D antibodies. Look at your chart, look at the B negative. B negative has B antigens. A and D are foreign, so you have A and D antibodies. So this means that you have to avoid A and D antigens because you will cause agglutination if you get an A or a D antigen. So let's go through our list. A positive, well, it has both of them, A's and D's, so you can get lots of agglutination. A negative, it has A's, you'll get agglutination. B positive, it has D's, you would get agglutination. B negative, yes, no A's, no D's there. Okay, AB positive, again, you would agglutinate with two of those, the A and the D. AB negative, your antibodies would cause agglutination with the A. O positive has a D. You would cause agglutination. O negative has nothing there. You can get O negative. So if you have B negative blood and you need a transfusion, you can get B negative or O negative. Okay, some of you might be thinking about universal donor. You may have heard of that. O negative is the universal donor. You can put it in anybody. Every person can receive O negative blood. The reason for that is they have no antigens. Antibodies bind to antigens. Well, if you have no antigens, there's nothing for an antibody to bind to. So it doesn't matter what kind of antibody the recipient has, they can't bind to a blood cell if there's no antigens on it. So antibodies cannot bind. So O negative blood will not agglutinate. There's nothing for the antibodies to stick to cause agglutination. There's also a blood type here that is the universal recipient. These people can receive blood from anyone else. So if you have this blood type and you need blood transfusion, you can get blood from anybody. That one is the AB positive. AB positive is the universal recipient. They have no antibodies. They have nothing to cause agglutination. Nothing is foreign to them. So again, this blood is not going to agglutinate because they don't have any antibodies. You can put anything in an AB positive person and they're going to be fine. There's another situation that comes up with blood types that has to do with pregnant women. There are circumstances in which the fetus can get hemolytic disease. And the good news is that today with modern medicine, we have treatments for this. But in the old days, it would cause miscarriages and stillbirths before we had treatment for it. So hemolytic disease occurs only under certain circumstances. The woman has to have negative blood type. And she has to have a child with positive blood type. So that's the only time it's an issue. So only women with negative blood type need to worry about hemolytic disease. And the child can inherit positive from the father. So if you have a woman with negative blood type and she marries a man with positive blood type, she'll have to get the RhoGAM shot in order to protect her children from hemolytic disease. So what happens here, we're dealing with positive and negative, so we're dealing with the D antigen and antibody. If we look at our pictures here, in the first picture, this woman is pregnant with her first child. This is her first pregnancy. So here we have a negative woman. This is her first pregnancy, and she's carrying a positive fetus. During pregnancy, mother and fetal blood don't mix. The placenta separates them. But during birth, there is some mixing. Fetal blood will leak into the woman. So remember, this fetal blood is positive. It has D's on it. And this leaks into the mom, who is negative. This sensitizes her. This sets off her immune system. Her immune system makes a bunch of D antibodies because this positive blood is foreign to her and her immune system doesn't like it. So it sensitizes her. She will make lots of D antibodies. This happens while she's giving birth, though. So even though she's making D antibodies, they can't attack her child because this child's on his way out anyway. So this child is fine because he is out before the mom's immune system can actually do anything. So women who have negative blood type can always have the first child. That will be fine. The issue comes with the second child. So now here you can see between pregnancies, here's all those D antibodies. She built up a bunch of them. She's now sensitized. Now we have her second pregnancy. And if the fetus is again positive, now those D antibodies you can see are crossing the placenta and attacking the fetal blood. Now, this isn't an issue with A and B. A and B aren't going to cross the placenta and attack the fetus. It's only the D's that do this. So now this fetus gets hemolytic disease. And this is fatal. So this will cause miscarriage or stillbirth of the fetus. So in the old days, before we had medical treatment, if you had a woman who was negative, married a man who was positive, they could have one child. After that, she would probably have miscarriages or stillbirths, unless if she had a negative child. So this woman could have a negative child and would be just fine. It's just a negative woman having a positive child that's an issue. So today we do have medical treatment. And that medical treatment is RhoGAM. So now anytime a woman who has a negative blood type gets pregnant, they give her a RhoGAM shot. So a pregnant negative woman gets RhoGAM during the pregnancy and again when she gives birth. What the RhoGAM does is it travels through the mom and into the fetus. So they give her the shot while she's pregnant. The RhoGAM comes in and it coats the fetal blood cells. So the RhoGAM goes to the fetus and it coats the fetal blood cells. It's like camouflage. Then when the woman gives birth and that fetal blood enters her body, these cells are camouflaged. They're coated in RhoGAM. Her immune system can't see the D antibodies. It doesn't see the D antigens. It doesn't detect that they are there. So because the RhoGAM is camouflaging those fetal red blood cells, when she gives birth and the fetal blood enters the mom, her immune system doesn't know. They are hidden from her immune system. So she does not become sensitized. She does not make the D antibodies. So this, if the woman gets the RhoGAM shot, that would not happen. There would not be those D antibodies there. Then when she gets her second pregnancy, there's no D antibodies to go attack that next fetus. So the point of the RhoGAM shot is to protect your next child. The first child's going to be fine anyway because he's going to be born and out of there by the time the immune system makes all these antibodies. The shot is protecting the next kid. And every time this woman gets pregnant, she'll get the shot again. Because let's say she's having her second baby now. You would get the shot, coat those blood cells. Then when this baby's born and the blood enters the mom, again, it's going to be hidden from her immune system, so she won't make those D antibodies, and that's protecting child number 3. So you just keep going on. Every pregnancy, you get that shot, and it's always to protect the next child, not the current one. The current one is born and out before the immune system has time to react. We are ready to finish up our chapter now by seeing what happens when you get a cut and how you stop bleeding. So we're going to talk about hemostasis. Heme refers to blood, and stasis means stand still. So this just means that you stop bleeding. And in the last one, I mentioned agglutination, and not to confuse agglutination with coagulation. Coagulation is a part of hemostasis. Coagulation means you form a blood clot. So first we're going to look at an overview of hemostasis and what happens. So we're going to begin here with number 1 is you have damage to your blood vessel. You have a cut and you are bleeding. The walls of the blood vessels contain collagen fibers. So there is collagen fibers here in the walls of your blood vessel. As long as your blood vessel is intact, those collagen fibers stay inside, right? Nothing is contacting them. The walls of the blood vessel are very smooth and slick. So out here, it is very smooth and slick. But when you get a cut, those collagen fibers are exposed. And this is going to be key because this is what the platelets stick to. Okay, so you have a cut, collagen fibers are exposed. The first response your body has to this is vascular spasm. So now these next set of pictures are your responses to the cut. So we're going to have vascular spasm. You can see here the blood vessel is constricting. It does this to reduce the amount of blood being lost through the cut. Next is when those exposed collagen fibers come into play. This is platelet plug. Platelets are flowing in your blood, so you constantly have platelets flowing around as part of your blood. When there's exposed collagen fibers, the platelets stick to them. Then the last thing that happens is coagulation. You form a clot. And then this clot plugs up that hole, and then you're no longer bleeding. And then you can begin the healing process. So we're going to look more at the blood clot and how that forms. First of all, let's look at the composition of a blood clot. Here is the clot. A blood clot is a web of fibrin with formed elements trapped inside. So if we look closely at this, you can kind of see this web, these strings here. This is a protein called fibrin. Kind of makes me think, remember the Spider-Man movie where there was the Spider-Man and there was that black gel that would get on him and it would grow on him and make a web on him? That's what this reminds me of. So a clot is a web of fibrin, which fibrin is a protein, and it traps formed elements, like bugs getting trapped in a spider web. And if you remember from the very opening of this chapter, formed elements are the red blood cells, white blood cells, and platelets. So all three of those, if you look in here, there's red blood cells and platelets, and maybe a few white blood cells get trapped in there. So that is your clot. So now we need to see how you get to the clot. So notice you have all these things here, these factors. If you look along, you've got factors everywhere. Think of this like a chain of dominoes. If we have dominoes, and you know how you knock down the first domino, and that makes all the others fall. That's how coagulation works. We're going to start off here with a cut, and we're going to end here with a blood clot. These dominoes are factors. Factors are proteins that are in your blood. And they are made by your liver. And they're inactive. So like just when these dominoes are standing up, they're inactive. Or sometimes you can think of it like having a can of SpaghettiOs in your kitchen cabinet. It's inactive. It's there when you need it. So that's what the factors are like. They're these proteins that are made by your liver, they're put in your blood, and they're inactive. And they're just flowing around as part of your blood. When you get a cut, you activate the first one. Well, that's like knocking down the first domino. And that activates the next, which activates the next, which activates the next, and so on. So that's what you see going on here. Here you have all these factors activating the next. You begin here, you have your platelets. They activate factor 12, which activates factor 11, which activates factor 9, which activates 8, which activates factor 10. Notice also along the way you have calcium sprinkled in here. If you remember back in chapter 7 when we were talking about blood calcium, and we said that one of the reasons you need blood calcium is in order to form blood clots. So also along the way here you have calcium is needed in order for some of these dominoes to each knock down the next. So you had these factors from your liver. When you get a cut, they begin activating each other. So a cut, the factors activate each other. Okay, when you get to the end here, the last couple of them are thrombin and fibrin. So the last domino is going to be fibrin, because this is the web that catches the formed elements. And the one that activates fibrin is thrombin. So you get through all your factors. You have prothrombin activated to thrombin. So its name is prothrombin when it's inactive. Its name is thrombin once it's been activated. So you can think of it like when the domino is standing up, it is prothrombin. And then when the domino falls down, it is thrombin. Okay, then you have fibrinogen. So when the domino is inactive and it's standing up, it's fibrinogen. And then when thrombin knocks it down and it's active, it is called fibrin. So prothrombin and fibrinogen are the inactive forms. Thrombin and fibrin are active. Thrombin is what activates fibrin. So you go through your factors. Factor 10 activates prothrombin activator, which turns prothrombin into thrombin. Thrombin then turns fibrinogen into fibrin. Fibrin forms a web, catches the formed elements, and you get a clot. So that's that whole chain reaction to make a clot. And remember that you need calcium in the blood in order for this chain of dominoes to work. Okay. Once scientists understood how this worked, then they can figure out ways to manipulate it. So sometimes you don't want a clot. Some people have problems with clotting. Okay, you can get unwanted clots. Ideally, they just form when you get a cut and you need it in order to stop bleeding. But you can get unwanted clots. And unwanted clots can cause stroke. They can cause heart attack. Because the clot can form, it can break loose, and then it can get stuck somewhere else in the blood supply, and it's going to block off blood to part of the body. So a stroke is when you block the blood to the brain. And a heart attack would be blocking blood to a part of the heart. So people who are at high risk for these conditions can take medicines to reduce their ability to make blood clots. Okay, so Coumadin is a common one, and it's also warfarin is the actual chemical, Coumadin is the brand name. This is a very commonly used anti-clotting medication, and it acts on the liver. So remember those factors. You need those factors. Those are the proteins in your blood that activate the thrombin, which then activates the fibrin. And remember that factors are made by your liver. Well, in order to make factors, your liver uses vitamin K. So the way Coumadin works is this medicine blocks vitamin K from the liver. So if you're on Coumadin, vitamin K cannot get into your liver. And if your liver can't get vitamin K, it can't make the factors. And then if you don't have factors, you can't activate thrombin, you can't activate fibrin, and you can't make a blood clot. Another common one is aspirin. If we look back up here, notice the platelets are what activate the first factor. So that's kind of the very first thing here in our chain of dominoes is the platelets activate the first factor. Aspirin blocks this. Aspirin acts on platelets. And it stops the platelets from activating the first factor. It stops platelets from secreting chemicals. And these chemicals, what they normally do is attract more platelets, so platelets stick to each other once they're active, and they activate the factor. So it stops the platelets from secreting chemicals that would cause the platelets to stick together and activate the factors. So back up here in the coagulation process, if you take aspirin, you stop that first domino from even being knocked down. And if you take warfarin, you don't have the dominoes. They're not there to be knocked down.